I'm drawing 9 graphs here, 3 by 3. Yes, I invite you to draw 9 as well. In the top row, we're going to do our position versus time, affectionately known as PT graphs. Beneath that, we're going to get our VT graphs going on. And beneath that, our AT. Let's start with, I think the last example I gave you the other day for position versus time looked something like this, approximately x squared. And if you graph the slope of a position versus time graph, then that's velocity versus time. For you calculus people, that would be the first derivative. If you take the first derivative of x squared, you get? Anybody? What's the derivative of x squared? Yes. Too early. 2x. 2x looks, something like that. It's a straight line in the positive direction. And that makes sense. If you're not a calculus type of person, just think about it. The slope starts positive, and gets a little bit more positive, and a little bit more positive, and a little bit more positive, and a little bit more positive. So the slope of your velocity versus time graph is going to get a little bit more positive, and a little bit more positive, and a little bit more positive, and a little more positive. Then if you take the slope of this, you get the AT graph, also called the second derivative. You get the acceleration versus time graph. In that case, our slope is constant. It's positive, but it's not changing. So your AT graph would look something like this. Constant, unchanging, positive. All right, what if our PT graph looks like this? Constant velocity in the positive direction. If I took the slope of that, it would be a constant positive number. So my VT graph would be in the constant positive, like that. And if I took the slope of that to get my AT graph, it would be a big fat 0, because the slope of a flat line is 0. So down here on my AT graph, I'm going to draw a line just for the sake of drawing it, but it's going to be 0. You can see me darkening the x-axis down there at the bottom. Position versus time graph, if you are staying in the same spot, your velocity is unchanging, so that would the VT graph would be 0, and then the AT graph would also be 0. What I'm doing here is going through the basic scenarios, just so that we're clear on the relationship between these different graphs representing simple movement. Now I'm going to go to a new slide and do 2 more of the basic graphs. So I'm going to draw 6 more, showing 2 more scenarios. PT, VT, AT. Oh, I'm sorry. That's a V. All right, let's talk about negative. Let's move in the negative direction. Let's have our walking man walk backwards towards the other brick wall. He's moving backwards there. Now his velocity is constant because the slope is unchanging, and it's also negative. If you took rise over run in that situation, it would be a negative slope. So let me actually redraw this. Don't erase it on your paper. You'll be fine. Just add a lower y-axis. Let me show you in a second, like this. Your slope for the oh my God, I'm sorry guys, I'm tripping here. Your slope for the VT graph would be a constant negative. And then your AT graph would be a 0, because the slope of a straight line is 0. I'm going to do the same thing for these next 2 graphs. I need to erase what I already drew and draw one with negative y values. because I didn't do that the first time. In this final example, I'm going to add another curve. This would be negative x squared, approximately. And if you look at the slope of this one, I always like to start at the beginning and just think about it. Early on, we got a negative slope, and then it gets more negative, and more negative, and more negative, and more negative. So if I'm graphing that slope, i.e. the VT graph, we're starting negative, and then we're getting more negative, and more negative, and more negative, and more negative. So it would look something like that. And then if you took the slope of this, it would be negative, but it would be unchanging. It would be the same number just forever and ever and ever, which would be negative. So your AT curve would look something like this. It would just be a flat negative line. So cool. Those are the 5 essential scenarios, as I like to think of them. I'm going to erase this and talk about going the other direction. Am I going too fast? I'm sorry. Can you look? Evan, do you have it? Evan, are your notes complete? Okay. All right. Now, let's go the other way. I'm going to put the 80 on the top this time. Then the VT. Then the PT on the bottom. And let's start with our first examples, where our acceleration was a constant positive, our velocity was increasing, and our position was approximately x squared. Now there's a way to go backwards, guys. In order to go the order that I did on the previous 2 examples, I was taking the slope of one to get to the next, and then the slope of that to get to the next. I was going in order of derivatives. But you can also go backwards. What's called integration. You can go the other direction too. The opposite of taking the slope would be to take the area under the curve. So, for example, acceleration time graph, if I took the area of this rectangle over that certain amount of time, t, the value of that would be equal to the slope of the VT graph. And if I take the area under this curve, if I did my 1/2 base times height, I would get the value of position. So it's a two-way street. If you're going in the direction of position to velocity to acceleration, you take the slope to derive the next in the sequence. If you're working backwards, you can simply take the area under the curve to arrive at the previous. And then if I took the area under this curve, oh, I'm sorry. Yeah, that's it. Any questions? Some of you might have seen this before. For some of you, this might be new. We're going to do some work problems now to work through this. I'm going to stop the recording.